So impact printing is a new method for additive manufacturing, and the goal is really to enable a really high volume and efficient additive manufacturing method that can not only be economically viable because it's fast, but also that can really move beyond the kind of constraints that we've been faced with by only using industrial robots. So we ultimately wanted to develop this additive manufacturing method for earth-based materials, but to also transfer it from off-site prefabrication to on-site using large-scale autonomous construction machines. So when we began the project 4 years ago, the first thing was to benchmark the kind of criteria that we needed to achieve in order to develop a process that's capable of industrialization. So in order to make something very low cost, we really need to reduce the dependency on skilled labor. We need to really think about efficiency. So in terms of build rate, the target build rate was 1 cubic meter to 2 cubic meters per hour. We need to really also not use custom formwork, and then also keep in mind the embodied CO2 or the greenhouse gas emissions from the processing that is aligned or underneath with the process. So as I mentioned, we wrote this grant in 2020, and we basically there were 3 different chairs involved. So I'm based at Gramazio Kohler Research, and Kunal, Ananya, and Victor did a lot of work supporting. Kunal and I worked directly together, and we're doing the spin-off together, which I will present at the end. And we work directly with the Chair of Sustainable Construction, and their expertise is clay-based and alternative materials, as well as life cycle assessments. And the Robotic Systems Lab, you may know them because they're doing autonomous legged robots. So the Animal was a spin-off that came out of their lab, but they're also doing autonomous construction machines. So the autonomous excavator was developed through their lab since the last 10 years. We worked a little bit with WASP to develop some custom hardware. So Max is in the room. We met with them. I can show you a little bit about how we worked with them. And then Eberhard is a local leader in circular supply chains in Switzerland, and they donate a excavated material to us at 0 cost. So first, I'm just going to show you the project video. I'm sorry that the audio is not playing, but it's very loud noise. But basically, we have a custom mechanism that shoots material with very high velocity. So we're shooting very dense, high yield stress material at about 10 meters per second. And when we do that, basically, you can enable a bond between multiple parts. The material is sourced from Eberhard, so it's 75% excavated material. We need very little additives because we already start with a high yield stress. And we've basically mounted and integrated the tool on the prefabrication setup in the RFL to investigate different architectural and structural forms through the MAS teaching. And we've also started to investigate mounting the custom tool also. Oh, sorry, I forgot the order of the video. So through the MAS teaching, we also developed custom surface finishing strategies. So here you can see a robotic process that scans the very textured geometry, and it basically applies a clay-based plaster onto the surfaces after they've been cured. So this is a few weeks after production. And this enables us to achieve a very, let's say, commercially viable surface finish. So as I mentioned, the goal of the project was to transfer our process from on-site to off-site. So we recently integrated our tool on the Menzimuk excavator, and this enabled us to actually build a structure outside the RFL in a kind of semi-structured environment. And this Menzimuk can actually hold a tool up to 4,000 kilograms payload, which is a huge opportunity in terms of rethinking material processing strategies from additive manufacturing. So they have also a trajectory following controller that has less than 3 centimeters tolerance. And I'm going to go a little bit into detail about the kind of control strategies that we use on our side for synchronization with the tool. And here you can see a LiDAR that's actually used for the ICP localization of the heap in the map of the external environment. So this was the demonstrator that we just produced. It's about 3 meters tall, and we produced it in 8 days of construction. There are some things that are not fully automated in our process, such as material delivery, but that's something we're working on now. So the main process benefit of this type of additive manufacturing, especially compared to extrusion-based manufacturing, is that we can enable mechanical bonding with materials that are extremely high yield stress, so greater than 28 kilopascals, and they basically wouldn't be able to be pumped. So they're kind of outside the range of delivery from a pumping system, probably even with rheological control. But we don't need that because we can basically take very dense materials and we can precisely control how fast we deposit them. And with this, we can actually deposit material with a high enough yield stress that it already can withstand several meters of vertical buildup. So this is a huge benefit for additive manufacturing because we basically aren't relying on the material, the rapid curing and the rapid green strength development of a material. So now you saw the kind of current state of the research. I want to go backwards and show you kind of the origins of the project. So I began 4 years ago, before we got this ETHZ grant funding, and we began with a very simple question: is can we project dense material with high velocity, high efficiency, and high accuracy at the full scale? So here are two different shooting mechanisms. Maybe they're not playing, but one is... Okay, well, anyways, I fast forward. Basically, we started with one belt-based system, which basically would have two belts that are rotating continuously. This means that you could enable a very fast cycle time. And we basically upscaled this concept. The target cycle time that I mentioned before is based on a build rate of 1 cubic meter to 2 cubic meters per hour. And so we were basically able to take this two-belt concept, accelerate parts, and achieve a very high controlled velocity, which we later improved in terms of accuracy. Then there is the question of establishing the yield stress domain. So yield stress is the resistance of a material to deformations. And this is one of the most important material properties to control in terms of 3D printing, because you need to accelerate the yield stress in order to resist plastic failures from the weights above. And what we found in very early experiments is that we can increase the yield stress and shoot at a higher deposition velocity. And this basically means that if you can withstand the yield stress from shooting, you'll also be able to withstand the yield stress from many, many layers of vertical buildup. So basically, we established a kind of relationship that basically we're always aiming to start at greater than 28 kilopascals yield stress. So we had kind of humble beginnings in terms of machine and human interaction. So before we developed all the other parts, we were manually feeding, and we mounted this high payload tool on the Z-axis kind of Goodell tower that we have in the RFL. So in terms of hardware, we basically had to develop a modular approach of our hardware for the two construction scenarios, both prefabrication and on-site construction. And then we also had to develop a kind of material processing strategy. So in the beginning, we were aiming actually to mount a high payload tool directly to the gantry mount in the RFL. But we realized actually it's quite tricky because of the way the RFL was integrated. So we actually ended up spanning between two different robot mounts and building a bridge structure. And then we took that volumetric massing of our tool and also implemented it on the Menzimuk. So the three subsystems are material delivery, the impact printing tool, and superstructures. And maybe if I go a little bit more into detail, you remember the shooting mechanism. This is coupled with a portioning mechanism, but also basically a batch mixing system and extrusion system. And these are actually earlier versions of the tool because we did patent the tool, and so I'm not showing the kind of final versions. But this is the final hardware, and here you can see it's mounted on the bridge between two industrial robots. So then we took the same massing, and then we built also a large, heavy massing that would protect it and enable it to be also mounted on the autonomous excavator. So I'm going to kind of hurry through some of these other slides. I think I only have 15 minutes. In terms of software control and integration, we asked ourselves the same question. How do we develop a software architecture that would enable us to easily move the process from being compatible with industrial robot controllers, but also autonomous machines? So our software architecture uses ROS as a high-level middleware, because ROS is the standard, especially in robotics research. And we basically have a high-level controller that's looping through positions, and it's communicating back and forth with a tool controller. And the tool controller is running a state machine, which is basically just looping through states at a really, really high frequency. And then the high-level controller takes the same kind of data structure from the design environment, and then it speaks with either the Menzimook platform or the ABB robot control software. So one of the big challenges is that we're not approaching extrusion-based 3D printing with a tight synchronization between the material delivery and the robotic system. Actually, when you extrude through a hopper-based strategy, you get actually a decrease in extrusion time. So we developed something to synchronize these two systems, which is based on online linear regression. So as you extrude, if you run at a constant velocity, you'll actually get it'll take longer to extrude. So basically, we predict how long it will extrude with linear regression. And then actually at the cutting mechanism, we hold the part until it's at its exact moment when it needs to be dispatched. So with this method, we have kind of a desynchronized synchronization. So our robot can move at one speed, and our extruder and cutting mechanism can move at a different speed, but we still enable pretty precise synchronization between those two systems. And then the software for both scenarios looks pretty similar. We basically just have an exporter, which exports very specific information, spatial information about each part, and then also the synchronization data that I mentioned earlier. So the material that we are using, I won't go into too much depth, but I think one of the problems with extrusion-based 3D printing is that you actually have to accelerate the material yield stress with additives. We are using mostly a excavated material that's coming from Eberhard, and we're actually using only a very small percentage of lime. And I'm pretty sure we could actually even minimize it entirely, because we can start in such a kind of stable state with the material. But that means that we're getting very close to an unstabilized earth-based mixture, which means it's fully recyclable. Right now, this mix has around 2 megapascals of compressive strength, but we're currently thinking about other mix designs. How do you vary the granulometry to get better results? And then also, how do you enhance the mechanical properties with surface finishing materials that might have a higher compressive strength? So these are some of the explorations that we did in the context of teaching. This was published this year at Fabricate, so feel free to look into that publication. And we just finished the heap demonstrator in February, and we will publish that shortly, hopefully. So this is the current state of the accuracy that we can achieve with our prefabrication-based approach. This is a huge breakthrough because we produced this in one session, so it's 1.85 meters tall, which you couldn't do with extrusion-based 3D printing in its current state, because you would have to pause to accelerate the grain strength. Right now, our cycle time is around 7 seconds per part, but we have only one motor that's driving our whole extrusion system. We're trying to reduce that to around 2 seconds per part. We have a few different optimization strategies, but I think eventually we will be able to match our target's construction rate of 1 cubic meter per hour. And this is really a question of scalability, because if you want a really industrialized process, not only do we have to print fast, but we also have to be able to print high immediately. So that's the main benefit of our process, is that we can immediately build vertically because we already start with a high yield stress. And now it's a question of how fast can we print. So how do we optimize our motor controller, our extrusion system, our control logic, and etc. So as I mentioned before, I'm just going to quickly end with our spin-off plans. So we aim to commercialize this technology. And so right now, Kunal and I have been working quite a lot on the business plan and a kind of market entry point. So we plan on entering the prefabrication market. And we have already funding through Bridge, which is one of the big transfer funds in Switzerland. And our concept is to develop a very streamlined-based approach for being very compatible with existing prefabrication-based systems. So to combine, for example, timber with our infill material and to implement a kind of plug-and-play logic so all the detailing makes it compatible with other types of prefabrication. So here you can see kind of some of the prototypes that we've been working on. Our method also has a high level of processability because basically we start in a high yield stress, but then we cure slowly. So that means we can wire cut, we can detail, and we can also, as I showed before, we're working on also robotic surface finishing. So here's our product sneak peek. We're still developing these. We're looking for, sorry that the video doesn't play very well. But we aim to incorporate actually quite soon. So I'm happy to hear any feedback. If anyone has any names, suggestions, ChatGPT has not been very helpful on that regard. But yeah, that's the conclusion. And I look forward to discussing with you.
So thank you very much, Lauren. Any questions from the audience? I'm starting from the back and coming from.
Hey, hello everyone. My name is Emric from Montreal, Canada. I have a question. I see right now your system seems to be integrated to structures. Are you planning in the future to implement solutions for thermal bridges and to add rebar in the system to make a building itself?
So there's a few strategies for the tensile reinforcement. One, with the prototypes you see on the screen, with the timber, our goal is actually to use the timber as the main load-bearing component so that we can accelerate a product that is easy to do certifications for. So we rely even less on the earth as a, let's say, load-bearing material. Then we can also test fibers in the mix design. What we're more interested in terms of reinforcement is doing a mesh reinforcement. So looking at glass fiber meshes and then flax fiber meshes. And we're actually going to integrate it into the process. That's our next plan in terms of testing. In terms of really high mechanical, let's say, tensile reinforcement, we do have the benefit that you can basically really process. We're basically milling into the material after we produce. So this is a huge benefit that if we wanted to do tiebacks or you wanted to put something horizontal between the layers, it would be very easy to do that. So this could be, for example, I'm not sure that using steel reinforcement is the right solution, especially because of corrosion. But we do have a lot of process potentials for doing multi-layered structures, for doing tiebacks, for integrating things in the material. And I think the first reinforcement approach is going to be this tensile mesh reinforcement.
Yep, thank you. Hey, Lauren, thank you for the talk. I have a very dumb question, I think. Now that you focus on prefabrication, my question is why you print vertical and not horizontal?
I think this is a very good question. I think if you are doing a flat wall, we could test doing printing into a mold or printing flat. Our competitive advantage, especially against other types of printing, is that we can build vertically fast, whereas others can't. So I think it's about also using our method strategically. Prefabrication is the market entry point, but we're still thinking like printing in the building site as just, that's not technically ready enough now. But I think this is a good point, and more than one person has mention this. I think the process of lifting it back up, it only works, of course, if it's completely flat, because otherwise when you have any curvature, then that doesn't make any more sense anymore.
All right. You had a question.
You mentioned that the ultimate goal is to move the process on-site. And I'm interested, what's the maximum scale of building you envision there? How many stories do you plan to build up with larger hardware to carry the system?
So the Menzima can reach, we did a reachability study, and we can reach up to 6 meters. So the hardware limits the scale. I think in terms of buckling stiffness and the mechanical properties, rammed earth structures have been several stories. And also you build thicker, so you have already a bigger moment of inertia to basically build high. I think 2 stories is basically the maximum that we are pursuing. So we did 3 meters already. I think we could probably do 5 to 6 meters in the next phase. I think now it's about balancing what we develop for commercialization and what also could keep being developed in terms of research.
And second related question, for integration with different structural systems, like if you have a timber frame or something, have you investigated non-vertical shots? Because everything you've shown so far, the clay projectile goes straight down. Yeah. Is it an option to like diagonally shoot it against the framework or something?
Yeah. Basically, it's kind of tricky because I think when you are shooting with such a high force, I would avoid shooting where you induce a very high shear force in the material. Mm-hmm. But shooting against something, I think, is smart. I think with the Menzimuk, with the 3-axis gantry system, we don't have orientation control. With the Menzimuk, we do have orientation control. And so if we did another Menzimuk demonstrator, we could investigate shooting against angled surfaces, or also doing slight inclinations when it's strategic. Yeah. So that's something to investigate, but I wouldn't shoot at an angle when it's freestanding at such a high velocity.
Yeah. Thank you. It's a really interesting approach.
Anything else from the audience? Yeah. Thank you. Thank you for the interesting talk. I have a question about the specific advantages of this shooting technology in comparison to stamped clay or Stampflehm. If we're talking about prefabricated elements, probably I've missed the information during the presentation. In this case, I'm sorry, but yeah, thank you.
Stampflehm would need, you mean basically local robotic formwork?
What is prep?
Yeah, but then you need formwork, and we only constrain the sides, and we also. So the main benefit is that we don't need formwork, and we're still achieving compaction.
Wow. All right. No more questions from the. Oh, there is what?
Hi. Thanks for the presentation, Lauren, and the novel ideas. When you think about rammed earth, you normally think about something which contains a bit more mass, and the mass is used. So it's kind of a 2-part question. With the prefabricated system you're looking at here, I would ask, how would you foresee the mass being used? And secondly, so as a thermal mass or etc. And secondly, could you also foresee this being used in a infrastructural environment?
Mm-hmm. Once we've optimized our, let's say, material delivery rate, I think it makes, then doing large mass structures, I think is totally feasible. I think there's also possibilities for using our method, 2-layered structures where you then cast on the inside. I think that would be another typology to explore, where you could get huge thickness and mass. Some of the student explorations I didn't show in depth, but there is some columns that were infilled with gravel, or that could, basically the gravel was kind of supporting it on the inside, and then you could also fill it in later. So you could do kind of large, fill in the cavities with any sort of cast material. And then you have kind of a benefit where we still print fast, but then maybe with pouring or with casting, you can achieve even a higher, let's say, volume per time. So I think that's very interesting. I think the thickness of the walls here are only because we start with interior walls, and then we'll also do exterior walls. And so 1 to 2 layered structures. I think we need to figure out how we can have as much geometry control in terms of the thickness. Because when we have a 3-axis system and you have the taper, the part that's elliptical, your thickness is kind of constrained. But if you can orient them, you orient by a certain angle to match a certain thickness.
Yeah, he seems happy. Okay, if there's no more questions from the audience, I have a question.
Yeah.
You have a nice system to deploy a lot of material in quite short time, which is one of the weak spots of AM that we all experience in our work. And I usually use functionalization of the components as a justification for doing it with AM. So if I asked you to envision a functionalization you could imply into your work, because what we see here is rather conventional walls and some are bent. But if you could, implement some function for a building, what would you do with this technology and what would you implement there?
Well, I think it's a question of functionalization, like what functionalization we're discussing. Is it about high resolution? Is it a design intent, or is it aesthetics, or is it actually beneficial in terms of thermal performance, or in terms of ventilation, or I would question whether high resolution systems are always performative, or the main goal is performance. I think with our system, I think there's still a lot of it fills a niche where we can have customization, but with higher throughput eventually. And I think there's still huge customization potentials, even though we're doing in terms of commercialization, we're only extruding, so you just have 1 degree of curvature. But we've shown that we can build columns and we can build other types of structures. So I think what performances you're thinking about need to be clarified before I answer further. Because we can also do, we can't do holes in our walls, but we could also do multi-layered structures. Yeah, I think there's a lot of potentials.